since you got already tired today. So let's start slow. Let's see, where were we? So today we'll do section 3 of this of these lectures. So the goal is to understand a little bit what is going on in this Anderson-Lampert theory. Seems that today we'll have to switch to yellow mathematics, or green perhaps, since we ran out of white. Okay. So let me recall for you the theorem which I wish to prove. So let's say this is automorphisms of Cn. So essentially this was the theorem which I stated last time, that if you have n is always bigger than 1 in this theory, and you have a compact set in Cn, and you have a V, which is a holomorphic vector field, actually it's entire, so it's an holomorphic vector field on Cn, and we assume that the flow, so assume that the flow phi t z, so this is the flow in, we can think of real time for now. Later the time will also be complex, but for now we can think of real time. Assume this real time flow starting at time 0 at the point z exists for all z in k and all times from, let's say, 0, 1 interval. Okay, then we wish to show that each phi t, each time forward map, and so in particular phi 1, is a limit of automorphisms uniformly on this set. Then phi 1 can be approximated uniformly on K by holomorphic automorphisms of Cn. So as I said, this theorem is roughly 20 years old. This gives very good control of what you can do, what sort of, how can you move sets around in Euclidean space. It's somehow surprising that, since you will see the proof is really quite simple, it contains only rather basic ideas in the theory of ordinary differential equations. But the thing is that, so most people who study ODEs and dynamics and so on study maybe real dynamics, and so so in the real setting. And in that case, this is not a very interesting theorem, because you see, in the real case, you can always, when you have some vector field, you can always make it complete by modifying it out of some compact set so that it becomes 0 near infinity. And then, since it's 0 near infinity, so there it doesn't move, and then it's complete. And so such things are really sort of obvious. So probably for this reason, people didn't realize that this approach could be useful. There are much better theorems than this, but this is the one we'll need. Okay, now let me let's consider, before I start proving this, let's think a little bit. So what is again the flow? So the flow is a solution of the system of ODEs. Let's say you just write a derivative. So you want to make your variable to be time dependent. So derivative on time of each variable is this function aj, the jth coefficient of the variable, of all the variables. Okay, so this is for j equal 1 to n. So you have n equations of course, if you put time here explicitly, then you have to put time here. And then you wish that Zj at 0 is your given initial point. So the solution of this I will then write as phi t of Z0 is the solution. Okay, so by the existence theory, the solution always exists for small time. But you can also make time complex. In fact, if you can solve this equation by the same existence theory, if these are analytic functions, holomorphic functions, then the theory actually gives you local solutions for complex values of time. So always exists for t complex, t less than some epsilon, which is depending, of course, on the initial point. So let's say in some round disk, around 0, whose radius depends on a, and this is, of course, a positive number, depends on the point. Now, if you think of this system in real time, so in real time, we can extend the solution to so-called fundamental domain. Fundamental domain. So this is the largest domain, omega, in product R cross Cn. In this case, you could have, of course, any manifold here. So it's the largest domain, which, of course, contains 0. So it's an open set. In here, it contains 0 cross Cn, so time equals 0 always is there. So it's the largest, you get the largest domain for which this thing exists. And such that, of course, omega is a union. In this variable, it's a union of intervals. So omega is really of the form Tz, such that, say, z is arbitrary, but t is then between two functions, say alpha of z less than t less than omega z. So where these two, this is a negative function, of course, and this is a positive function. These functions can be also infinity. So it's so these numbers are positive real. This is a positive real number or plus infinity, and this one is negative or minus infinity. And since this is a domain, they have semi-continuity property. So this is the maximal domain. And now we say that such a vector field is complete. So V, which is a field with these components, like here, we say that V is complete in real time if this domain omega is everything. So this means if the flow exists for every real time, no matter where you begin. So such a field is called complete. But then, what about if you now look at your vector field and the fundamental domain in the complex time domain? Then it becomes rather complicated, because you see, by analytic continuation, you can propagate the solution to some Riemann domain in the T space. So now the T space is complex. So you will get by analytic continuation some Riemann domain, which, however, is not inside C, but over C. And these domains will, as your original point moves, your beginning point, these domains can change in a strange way. For instance, you can go from multi-value domain to single-value domain and so forth. So it's not a very good, it's rather difficult. You cannot say that the fundamental domain in complex time would be actually a domain in something, but it's rather sort of a Riemann domain over C cross Cn. But the problem is that it's not even Hausdorff. You have to actually work hard. Actually, Marco Brunella has a good description of this, how you define fundamental domain in complex time. I will not go very much into that, but I will say that if we can observe the following, that actually we can get, so if we look at this in complex time, if I write time as t plus is, for example, where this is real and this is imaginary component, then actually it's possible to understand the system as follows, that that the flow, it's easy to see that the flow for this complex time, at least if time is small, of my field V, can actually be written as a composition of a real time flow of V composed with imaginary time flow S of the vector field I times V, or rather J times V. So you basically, if V goes here, if this is V, then the J times V or I times V is just obtained by rotation by the complex structure. And so then you simply take flow in this direction and you compose the two. And this is how you get, at least for small times, you get complex time flow. So for example, if such a field is V complete, if V is if it's R complete, then it's then not hard to see that its fundamental domain in complex time is actually, let me call it omega C, is in fact union, so it will be something in C cross Cn, and it's a union of stripes. So you can write it as a domain of the form T plus Is, comma Z, where Z is any point in Cn. And again, here you could replace Cn by more general complex manifold. But and time is real time is arbitrary, of course, since I'm saying that it's R complete. But in the imaginary direction, it need not be complete. So the imaginary time direction is again between two numbers. So you have, say again, minus alpha. You can write like this. The t is between minus alpha z and plus omega z. And again, these numbers are up to infinity. Okay? So this means if you fix z, then you actually get a strip, a horizontal strip in the complex plane. If this is the t plus is plane, so here is the t direction, here is the s direction, and you get such a strip. So this value here is omega z, and this value is minus alpha z.
Is that double inequality? Shouldn't that be s instead of t?
Which one?
The last one.
Yeah, this is s, of course. Thank you. This is, of course, s. T is arbitrary, but s is between these bounds. So it's stripes, and these stripes vary. OK, so this is pretty easy to see, because basically, you see, as far wherever you can go in this direction, then you can go everywhere in the horizontal direction, and so on. And if somewhere else you could go up, then by adding this line, you could also come back. So it's just some argument with uniqueness that you actually get this kind of domain. OK, and now there is something interesting. Namely, that if you're really on Cn, then in fact, actually if you're on any Stein manifold, so on Cn or on any Stein manifold, it's easy to see by simple analytic continuation arguments that this fundamental domain in complex time is actually pseudo-convex. So it's easy to see by analytic continuation that omega c is pseudo-convex. So it means the same as domain of holomorphy. Okay, but this, so this is just by analytic continuation. They're rather easy arguments. And then this actually means that it's easy to see that this means that these two functions, omega and alpha, which govern this domain, are with appropriate sign are plurisubharmonic. So this is equivalent that actually negative of this function. So negative alpha z and negative omega z. And of course, by definition, they are all smaller than 0. That these functions are plurisubharmonic. That's equivalent to pseudo-convexity of this domain. See, but now there are no plurisupermonic functions on Cn which are bounded from above, other than constants. So it's a fact that every PSH function on Cn that is bounded from above is constant. In fact, this is true on many other complex manifolds, on some kind of big manifolds. Manifolds with this property are usually called Liouville. So you say that a complex manifold is a Liouville, or sometimes it's called a ultra Liouville. No, maybe just Liouville. If this is true, if every bounded plurisupermonic function is constant. So what we infer here is that these two alpha and omega are constant. But then, what does this mean? Well, this means that you can go, no matter where you begin in your space, you can always go in the imaginary time direction, at least for some fixed amount. Well, but then you arrive there, and you can go further for the same amount, and you can go further for the same amount. And so immediately you see that this really means that it's also that the flow is also complete in the imaginary time direction. So actually the conclusion is that this domain is then all of. So it follows that omega c is actually C cross Cn. And again, this would be true if I replace Cn by any Liouville Stein manifold. Stein, I need it here to make this argument for, and which I didn't do, but okay, so this means i.e. So the conclusion is that every R complete holomorphic vector field on Cn or on any Liouville Stein manifold is actually C complete. Okay, this is a rather simple result. It's actually due to myself from 94. There were some generalizations by Heron, Rosé, Heron, Flores, and Rosé. A bit later, I forgot the exact year, maybe 96, where they actually show that it's even enough to be R, if it's R plus complete. Okay, what does R plus complete mean? It just means you can integrate in positive, in forward time. Maybe not in backward time, but in forward time. R plus complete implies C complete. So you see, so the upshot is that when you're on Cn, you don't really have to distinguish these notions, R complete, C complete. And that's nice because this means that you get this flow now automatically. As soon as you have a complete field, you actually have it defined for all values of T complex. And then you can actually combine. If you have several such vector fields, you can compose their flows for different time variables. So you go for some time along one direction, then you switch direction, you go for some time in another direction, and so forth. So you get a big parameter space. Say parameter space, all these times are then some big Euclidean space. In this Euclidean space, you can pick many complex curves or higher dimensional submanifolds. So this actually shows that as soon as you have many complete fields, you also have many entire curves of automorphisms, because the flow, yeah, this observation I didn't do yet, but we can observe, of course, that the flow of any complete vector field, the flow phi t z of C complete holomorphic vector field is in fact a one parameter subgroup, one parameter, let's just say group, of holomorphic automorphisms of Cn. So it's so we have that phi t, where t is complex, is actually contained in out Cn. It's a 1 per meter subgroup. Of course, we have this. Why it's a subgroup? We have this law. That if you go for t plus s time, then this is the same as phi t composed phi s, and of course in the other way too. So it's a group. So yes, of course.
I don't understand the last result. What if we have something like a ball and a flow quantity inward?
Yes. Yes, of course. That's a good question. For instance, on a ball, on a unit ball, you can take a rotation field, which is complete. You can always, okay? But then the imaginary direction will point out. So in the imaginary direction, it won't be complete. Okay? So, but you see, ball is not Liouville. So this result does not apply on the ball. Here I'm saying that this result implies if you're on a Liouville manifold. So ball is hyperbolic, and therefore it's not true. Stein-Liouville, yeah, Stein-Liouville. So ball, of course, yes. If you look at the rotations of the ball, rotational field, it just makes circles, but then you go out while you hit the boundary pretty soon, or vice versa. You start with that one, yeah. So of course that's not true, but you really need, you see, you really need to make this argument that there are no bounded plurisupermonic functions, while on the ball you have plenty. Yeah. By the way, people in group theory have extended this result quite a bit. I mean, using this simple result, one can actually show that every action that on such a manifold, if we have an action of real Lie group, then it will extend to its complexification, of course. So, well, I don't know this theory well enough to really say anything sensible, but I know it's been used quite a bit, this observation, which is rather simple. Okay. All right, so all of this is pretty standard. But what we want to prove now, to prove this theorem, is actually the following. We want to show, well, we show two things. One is that you can always calculate the flow of a vector field by an iterates of a fixed map. So the idea of proof, so to prove theorem, we use, this is usually called Euler's method of integrating an ODE or a system of ODEs. What is Euler's method? So basically, you can state it as follows. Let's say that let's see, I didn't write this down. Yeah, okay, here is my Euler's method. So what is Euler's method? This you can find in my book, but it's actually very classical. You can find it in many texts. So all you need, so let's take this as proposition. So let's say A of t and z be a map. Let's say a C1 map from an open set U inside, now it will be inside the space R plus cross Cn. But again, this works pretty generally, so here you can replace Cn by any manifold you like. So it's an open set in U R plus cross Cn to Cn such that the 0, so 0 cross Cn is contained in U, and we have the following two conditions. So this map has the property that at time 0, sometimes I will also write it as a sub t of z. later it will be more convenient to write it like so. So I want that a of 0 z is z for all z in Cn, and the derivative on time at time 0 of a of tz is my vector field. So it's this column, a1 up to an. Okay? So what I have is a map which roughly behaves like, let's say to first order it behaves like V, because actually the flow of V has this property. The flow of V satisfies this, and its derivative on time by definition of the flow is just vector field. But now I'm taking any map which has the first order contact with its flow, with the flow of V. Then actually you can calculate the flow approximately by iterating this map. So then flow phi t of z, so this is the flow of V, is equal to the limit as the number of iterates goes to infinity. And now what I do, I take the map a of t divided by n. Okay, but then I take its nth power, nth iterate, which I'll just put n here. So what am I doing? I'm taking the map a for the time. I divide the time interval to a large number of equal length subintervals. So I take a of t over n. This is a map. It's maybe not defined everywhere, but I'll state. But then this is the nth iterate. So it's the nth iterate of a of t over n. So what I'm doing is, let's say I start somewhere here, and this is my trajectory. So I want to go here. Okay, so instead, I don't go. So first, I would have to come here. But instead, I do an error, and I come somewhere else nearby. So let's say this is a of t over nz. So I go here instead. I make a little error. Then I continue. If I apply a of t over n to this one again, I maybe come here, but in reality I should be there. So here is a of t2 over n, and here is a tn to power 2, and so forth. So in end, after n repetitions, you come here, but then the point is that this is not very far. And in fact, if the number of steps which you do grows to infinity, then you get this. You can specify this. So in fact, the limit, the convergence, is uniform on any compact subset of the fundamental domain of V. Well, but just in the positive time. I'm now looking at domain, fundamental domain in the positive real time. So in positive real time. You can also go in the negative real time, but that's easy. You can just replace v by minus v, and then you'll go in the negative time. So it doesn't really matter. Now this is rather easy to prove. I'm not going to do it here because it's really elementary calculus. You have to know. So basically you can think like this, that the error, so the idea of proof is that the so-called Lie series, which is really the Taylor series of the flow, which is usually called the Lie series, is Pt of z is z plus t times vector field at z, plus then the next terms will be something like this, t squared over 2. Then you applied vector field to itself. So you write usually v squared of z. So what is this? This is v applied to components of v of z. So it's just some vector again, and then you have higher order terms. So the general term in this series will be t to the n divided by n factorial v to the n of z. So all of this is actually O of t squared. And now we have also A of Tz is Z plus, by this condition here, is the same for A. Plus here I have little o of t. So you see that the error which you make in time t is little o of t. So the error in one step, if I go back to here, I divided t by n. So the error is of the order little o of t over n. But then I have n steps. So the error is n times o of t over n, which of course goes to 0 as n goes to infinity. Here this is actually not very precise argument, because to do this precisely, you have to analyze what happens when you okay, at one step this is correct, but in the next step you really apply these two estimates at different points. So you look at the real flow you apply to this point, while this map you apply to that point. And there is some distance between them. But you know, these are well-known estimates. How far do trajectories diverge? These are just consequences of Grenwald's lemma. So you can control how fast they converge. So morally speaking, what I say here is correct. But you have to do some work to see this. It's not difficult. OK, so this is one key idea in the proof. But now the second key idea now we observed, by the way, such a map is usually called an algorithm. So such A is called an algorithm for V. So of course, there are many such maps. But now we can observe that the following. Let's say that we have now two vector fields. So suppose now two holomorphic vector fields. Actually, this story has nothing to do with holomorphicity. This is a story for arbitrary vector fields on smooth manifolds. But since we are dealing with, I can put this in parentheses, with flows Pht and Ct, respectively. So Pht is the flow of V, Ct is the flow of W. OK, then it's easy to see that Pht composed with Ct or Ct composed with Pht, whichever one you want to use, is an algorithm for the sum. And why? Because you just, do I have Taylor expansion? Here is the Taylor expansion. So you start with this, then you have to apply Ct to this. But what you get this, plus then you have to add t times W at this point, plus the rest. But when you calculate t times W at this point, you Taylor expand. You apply W to all of this. So the main term is W on Z. And all these other terms become of higher order, because here you have an extra t. So basically, it's immediate that the flow, so i.e. the flow of V plus W at time t actually starts like this. Starts like this. And if you calculate this composition, it also has linear terms like that. OK. So you can easily get an algorithm for the sum. Of course, you can apply this to several factors. So this applies to finite sums. So if you take a finite sum of vector fields, you just take their flows, and you take their composition in any order you like. And this will be an algorithm for the flow. So it follows from this Euler's method that the flow of the sum is just, so consequence is that the flow of the sum, let me just write it like this. So this is the flow of the sum for time t, can be obtained as limit as n goes to infinity of phi sub t over n composed with c, or let's rather write it in a more consistent way. Let's say this is flow of v, here is flow of w. Let's always write it as phi and indicate upstairs. Okay? And then we iterate this to power n, and we apply to the initial point z. So we just take this time forward map, apply it nth iterate to z. So this is consequence of Euler's method. And why is this interesting? It's interesting because if you happen to know that these two fields are complete, so if v and w are complete, then then these maps phi t over n, and then these maps, then phi t v and phi t w belong to automorphisms. And so this is an automorphism, and its nth power is an automorphism. So what you see immediately is that the flow of the sum is actually a limit of automorphisms. So phi of v plus w is a limit of automorphisms of Cn. Of course, uniformly on compacts, wherever the flow exists. So uniformly on any compact where the flow exists. And of course, the same is true for finite sums. You can go a step further. You can also do this for commutators if you like. Sometimes in this theory, it's good to use commutators. In general, of course, it is not true that the sum would be complete. You can find immediate examples. It's almost never true that the sum of two complete fields is complete. But you have this statement, which is good enough for us. Okay, so there is a similar story for Lie brackets. So Lie bracket of two vector fields, I suppose you know this operation. You can also think of it as a Lie derivative of the second field along trajectories of the first field. So what you really do is you can define it like this. It's a derivative on time at time 0 as so you take phi t, flow of v. Let's say this is flow of v. And then you pull back by this flow the second vector field. You pull it back, meaning this is a diffeomorphism, so you actually push it forward by the inverse. Diffeomorphism, a biholomorphism in our case. Okay, so you get vectors in the same space. For fixed point, you get vectors in the same space. You get a path. And then you can differentiate it on time 0. So you get a vector again, and this vector is the Lie derivative. It's also the same as commutator. What's the story with commutators is that you can also write it as follows. So this can also be expressed as a limit, actually just as a derivative at time 0 of the following. First, you go forward with respect to v for the square root of time. So you start somewhere, and you go in the direction of v for square root of t. So you arrive to this point, phi square root of t z. Then you go in the second direction, in the direction of w field, again for square root of t. But then you go back in the direction of v field. So here I put composition with phi v for minus square root of t. So you go back for square root of t, and then finally you go back in the second direction for minus square root of t. Okay, so you arrive from here to there. But then you let time go to 0 and you differentiate this expression. And it turns out that you get this. So I mean, at each point, fixed point z, you have to put z somewhere here, right? Okay, so what does this tell you? Is that this expression is, again, if you call it ATZ, is an algorithm for the commutator, just because it has the right property. And again, you can conclude that you have formula like this, except that you have to use this map. So what you again conclude, I won't write down the formula, but you conclude that the flow of this guy, if V and W happen to be complete, then the flow of this guy is also a limit of automorphisms. So if R C complete, actually even R complete would be enough, but let's just call complete since we know it's all the same. Then phi t of the commutator is a limit of automorphisms. So if you put these two things together, you can actually see that if you take a bunch of complete vector fields and then start forming Lie algebra from them. So you take the Lie algebra span. So if you take V1, V2 up to Vk, say, which are complete, and then you form the Lie algebra span. So this means that you perform sums and Lie brackets iteratively, starting with these particular fields. So this is some Lie subalgebra of the Lie algebra of all holomorphic vector fields on Cn. This is an infinite dimensional Lie algebra, but here we have some subalgebra. And then the conclusion, the upshot of this stuff is that if you take any vector field here in this Lie algebra, and then its flow is a limit on compacts again of automorphisms of Cn. So you see we are now already well along the way improving this theorem. Because all what we have to show is that any vector field which I like, but here I will now switch to polynomial vector field because anyhow by approximation I can always assume this is a polynomial field. So now the key point to prove this theorem is just to prove that any polynomial vector field on Cn is actually in a Lie span of some suitable finite number of complete vector fields. And this result is actually the focal point of the what's called the Anderson-Lampert theory or the Anderson-Lampert observation. I mean, it's easy once you know what you're doing. So we have the following lemma that every so this is due to Anderson in the special case, and then to Anderson in Lampert. So every polynomial holomorphic vector field V on Cn is a Lie combination. Actually, it's even, in this case, we'll prove that it's even a finite sum. V equal V1 plus V2 plus etc. of complete polynomial vector fields. Okay, so this is what we can prove. If you use Lie brackets, it's even maybe it's even faster. But even for some, it's not hard to do.
Please.
Yes.
Can I put a question?
Yes.
If E and W are not complete,
If which?
what happen? So if are complete, then Phi is a limit of
Yeah.
If
Yeah.
are not complete, what happen?
Then you can't say much. No. Then you can't say very much. If you start with fields which are not complete, then who knows? But my point of this thing is that I will show that every polynomial field, most of them are not complete. Actually, I think it was already mentioned by Professor Servaux that, for example, on C2, if you look at polynomial vector fields on C2, very few are complete, and actually a classification is known by Marco Brunella. Marco Brunella has a complete list of complete fields, and you see that there are rather few. And I'll give you momentarily some examples of complete fields, momentarily. Some simple examples. But just the point is to show that actually every polynomial field can be written as a finite sum of certain special complete polynomial vector fields. In fact, these Vj's will be what is called shear fields. The simplest fields you can imagine. I'll define them in a moment. So there are OK, so once we have this lemma, we are done, right? Because what I told you so far, plus this lemma, you complete the proof immediately. Because let's repeat again how you complete the proof. You say, well, here I have an entire field. I approximate it by polynomial field. This doesn't change the flow very much. We can estimate how much. Then we deal with polynomial field. Well, then we decompose it like this, and then we can actually explicitly, if I reiterate what I said there, we can explicitly say that the flow of this guy is a limit as n goes to infinity of flows of these individual fellows for time t over n. Okay, and then you have to raise this to nth power. So you see each individual fellow here is an automorphism. You compose them, and you take the nth power. So it's still an nth composition, nth iterate. So it's still an automorphism. So this object actually belongs to the automorphism group of Cn. Of course, you see that you have really no control on this number. So this grows very rapidly, perhaps, if you want to approximate some concrete field times V. Okay, these are easy things to check. Again, it's complete. So it turns out that with such fields, we can build everything. So we can prove this lemma with such fields, where each of these Vj's here on the right will be one of these fellows. OK. Well, at this point, perhaps I wish to leave this. So let's go to the other blackboard. And now it's just some simple algebra to do. Maybe I introduce one more notion. I introduce the notion of divergence of a vector field. Well, the notion of divergence is, of course, the classical notion in Rn is that you take jth component, differentiate with jth variable, and add up, right? This is the divergence. So we can say the divergence of a vector field sum aj z partial on zj is a function that's defined as follows, which is just aj on zj. Okay, this is the familiar notion. So divergence of a holomorphic vector field is a holomorphic function. But actually, there is a more intrinsic notion of divergence, which you get as follows. So more intrinsic, which, by the way, I won't need, but just I wish to explain. You can start with any omega, which is an over-vanishing holomorphic n0 form. Holomorphic n0 form. So such a thing is called, where you're on Cn, for example, such a thing is called a holomorphic volume form. So of course, the standard one is just the standard is omega 0, which is just the product of differentials of coordinates. So just this you take as a standard one. Okay, if you have such an object, here n is the dimension of the manifold. You can be on any complex manifold, and you take such an, if you have such an object, so this you have if the canonical bundle is non-trivial, because is trivial, because this is really a section of the canonical bundle, such a form. Then you can define divergence as follows: that you take for any vector field, you simply contract this forum with this field. This means that you use, contraction means that you really use this field as one of the variables. So this is now an n-1 forum, because this acts on other vectors so that you place v on the first slot and then you place other vectors later. So this is an n-1 forum. You differentiate it back. So you get an n forum, but each n forum is a multiple of this non-zero n forum. So you get a function here, and this function you call divergence of your field with respect to omega times omega. So this is now a function. And if you do the calculation for this forum, you get really this divergence. So you can say that this is divergence with respect to the standard forum.
Could you
yes?
explain again this operation?
This operation here. This is called contraction or inner product. So basically you do this. So this should act on other n-1 other vectors, right? This is a forum. This should act on n-1 other vectors. So this you just define to be omega acting on this set of vectors. In reality, you wish to write here wedge product, right? Because it's an alternating thing. So it's just this. It's called contraction or inner product. This is a special case of a certain formula called Cartan's formula. Cartan's formula in general has an extra term here, which would contain the differential of this forum. But you see here differential is 0, because you anyhow have top forum. OK, so there is nothing there, no extra term there. Otherwise, you have an extra term. The extra term would be here. The extra term would be plus v inner product with a differential of omega, but this is 0. So this is a full Cartan formula. OK, now we don't really have to know all this. We just need to have this notion of divergence. We can observe that if v OK, now we can go to the proof of the lemma there. So to prove the lemma, so let v be any polynomial vector field on Cn. And now I can decompose it according to homogeneous terms. I can write it like this, where Vj is homogeneous of degree k, of degree j. So this is just writing a polynomial in terms of homogeneous expansion, nothing else. And then, of course, it suffices to prove the lemma for each homogeneous part. So it suffices to prove the lemma for each Vj separately, because then you just add up. So let's assume from now on that V is homogeneous of degree k. So can assume that V, which is sum Aj z partial on Zj, is homogeneous of degree k. So this means that each Aj is a homogeneous polynomial of degree k for each j. It just means that. OK. And now our goal is to write it, to decompose it into such special fields as we have up there. And here we use a little lemma. from algebra, which I won't prove. You can find it in any book on commutative algebra, for instance, in Zariski and Samuel or many other books, that in fact you can always pick. So there exist, the lemma says this, that there exist linear functionals lambda e of z. So this is some aij zj, j equal 1 to n, and finitely many such. So there exist finitely many linear C-linear functionals. And this number will depend on k and n. N is the dimension of this space on which we are, such that every homogeneous polynomial of degree less or equal to k can be written as sum of powers of these things. So can be written as p of z. So this is my homogeneous polynomial of some degree up to k. Actually, let's just say k here. But then you can do, of course, since we have finitely many numbers, you can do also for lower ones. Okay, so let's just say of degree k can be written as sum of some coefficient ci, and then these functionals to kth power. So each homogeneous thing you can decompose into powers of pure terms, meaning linear functionals. Okay. And we can also assume, actually, you can pick, so in addition, you can pick the lambda i's from any non-empty open set in, since they are functionals, I can think of them as being elements of the dual space of Cn. So elements of the dual Cn dual. So that means in any small cone you can pick them. And in particular, I can always assume, so we can assume that the nth coefficient for all of them is non-vanishing. And in fact, I can make it 0. So I can assume that ai n, which is lambda I applied to the nth unit vector. So I'll denote by En standard basis of Euclidean space. So this is nth unit vector, so that this is equal to 1. This is easily done. First, you have to arrange that it's non-zero. And then you can rescale so it becomes 1. So let's assume this lemma. And now I'll just proceed as follows. I will now apply this lemma first for divergence of my field. So I apply the lemma with k minus 1 instead of k. So apply the lemma to the function, to the polynomial divergence of v, which is homogeneous of degree k minus 1. Right? Because I started with something homogeneous of degree k, and you look at that operation of divergence. I just arranged it. I just erased it. But you see that you lower the order by 1. Okay, so I write divergence of v as sum of, let's say, di lambda I z to power k minus 1 is equal 1 to m. So maybe I have to pick m in such a way that it works both for k and for k minus 1, but that's not a problem. So I write it like this. But now we can actually, okay, now what I do is I now pick a vector VE in Cn, in the kernel of this functional. So such that lambda e of VE is equal to 0. And I can, in addition, assume that it's a unit vector. And then I define the following vector field. So for each I pick such a field. And then I define VI to be the vector field. So VI of Z is the vector field DI lambda I Z power k minus 1. And then I take scalar product of Z with VI. And then times VI. So this VI, I think, is a constant vector field. So just I identify vector fields with vectors, really, okay? So you see, this is of course homogeneous of degree 1, this term. This is homogeneous of degree k minus 1. So this is now homogeneous of degree k. And now there is an exercise for you to show that, just a calculation, show that divergence of this particular field. Okay, notice that this field is one of those upstairs. It's one of those W's there, right? So it's a shear. So this is a generalized shear. So in particular, it's complete. Okay, and then there is an additional exercise to show that the divergence of this field is actually equal to this function here without this term. Is equal to di times lambda I of Z to k minus 1. So it's equal to the ith term in this sum. This is quite easy, actually, if Vi, so you can use conjugation by SLN. Conjugation by SLN preserves divergence. So if you think that this Vi is the En vector, the standard vector in nth direction, then this variable here becomes Zn. And when you take divergence, you just have to differentiate nth component on Zn. Okay, so this Zn goes away, and you get this. And of course, in that case, this functional is just depending on Z prime. So it's an easy exercise. Okay, so what does this mean? It means that if I write, that I can write V as a sum of these guys plus something else. And this something else, so I can now write V as something else plus sum of these guys which I made here. Right? I can write like so. But now the calculation shows that divergence, if I apply divergence on the both sides, I get that I get the divergence of V. Divergence is additive, as you can easily see. So it's equal to divergence of V prime plus sum of divergences of VI. But just by my construction, this actually is the same as divergence of V. This is by my construction. So the conclusion is that this is equal to 0. Okay, so by doing this, I have reduced the problem to the case of vector fields with divergence 0, because I have written any V as good guys plus something I don't know. Okay, but now we do something similar. So I write now V prime in components. So I write vector field in components like this. And then I just use the lemma again for each component except the last one. So I take an index j from 1 to n minus 1. And I write Vj prime as a finite sum of let's say Cij lambda I of z to power k, and index runs from I equal 1 to m. I just use the lemma. This is by lemma. And now we're almost done, because now we define the following field. Vij, I define it to be Cij. So for each of these terms, I'm going to make a field. So Cij, lambda I z to power k. And then here I put jth standard vector. So this is the vector 0, 1, 0 in the j slot, okay, minus this number lambda I ej en. Okay, so essentially I put 1 in jth row and minus lambda I to ej on the nth, in the nth row. Okay, and this function in front. Okay, now you immediately see that this vector, if you think of it as a vector, okay, this is a vector in Cn, but this vector is in the kernel of lambda I. If you apply lambda I to this, you get lambda I of ej minus lambda I of ej, lambda I of en. But lambda I of en is here, is equal to 1. So this vector is in the kernel of lambda I by my construction. And so this means I have a constant times this function times a vector in the kernel of this function. So this means if we look upstairs, that I have a vector field of the first kind there, just in the middle. So it's a function of lambda of z times a vector. And the vector is in the kernel of lambda. So this is a shear of the first kind. Actually, it's a shear with divergence 0. Shear of the first kind. Okay, by doing that, we now write v prime as the sum of all these guys which we made. So here I runs from 1 to m, j runs from 1 to n minus 1, plus something else. Okay, but now you see what have we done. By this construction, if you look at the jth components, they add up actually, I mean, if you add up over I, if you fix j and you add up over I, then the jth components are just, since we have ej here, there are just these functions. These functions add up to the jth component of this guy, which means that these two vector fields have the same jth component for every index up to n minus 1. So it means that this last thing is actually just a function, say h of z times the last component, say times en. Okay? It's just something in the last coordinate direction. Well, but now we are done, because now one more step. Okay, now we know that 0 is divergence of v prime. These guys also have 0 divergence. So it's equal to divergence of v, of w. Okay, but divergence of w is equal to, so I have this field. So it's actually equal just to derivative of h on the last variable. Okay, and this is of course an identity. So this means h is independent of Zn. So this field w is actually h of z prime times En. And it's again a shear of the special kind up there, and that's it. So we are done. Well, we did some algebra, but nothing really too bad. Okay. So that completes the proof, and that completes the proof of that theorem. As I said, if you use commutators, then you can actually do a little better, faster. But still, it's not trivial I should say that Drover-Rollin has extended this notion quite a bit by very systematically using commutators. So Drover-Rollin, actually he did this in the PhD thesis in 1997, but then he had a series of papers until about 2003 perhaps. So he introduced the so-called density property. So what would you say? You would like to say you can define this property for any Lie algebra. Let's say that you have G inside holomorphic vector fields. Here you can actually take any complex manifold. Now this theory is not interesting for compact manifolds because on compact manifolds every field is complete for obvious reason. But there are very few vector fields in general. So this is interesting theory for example, affine algebraic varieties or affine or Stein manifolds and so on for open manifolds. So here you could take Lie algebra, Lie subalgebra of the Lie algebra of all, or in very often people study the algebraic case. If X is an affine algebraic manifold. So if X is something in a Euclidean space, affine, defined by polynomials, affine algebraic, then you have algebraic vector fields on it, and this form Lie algebra, or holomorphic vector fields form a larger Lie algebra, and you look at some Lie algebra in it. And then you look inside this Lie algebra, you're interested if you have any complete vector fields. And you say that G satisfies the density property if the Lie subalgebra, let me just write GC of G. So this is some Lie subalgebra of C of G, which is generated using sums and Lie brackets by the complete vector fields in G, by the complete vector fields in G. Okay? If this subalgebra of complete ones is dense in G. Uniformly on compacts, in the topology of uniform convergence on compacts. And in the algebraic case, you actually require that the two are equal. So the algebraic density property actually requires that G, C just equal to G. So this, you would say that G satisfies the algebraic density property if the Lie span, using sums and Lie brackets of all the complete guys which it contains, this is GC, is actually equal to all of it. And you see, the theory which I was explaining today actually works in all such cases, because what does it tell you? It tells you that the flow of anybody here consists of automorphisms. And not of automorphisms, but is approximable by automorphisms. If you take anybody here, you can write it as a Lie combination of complete ones, and therefore we know by our theory that the flow is actually a limit of automorphisms. You have to be aware that even in the algebraic case, the flow will generally not be algebraic. They will be entire. But you can also speak of so-called nilpotent fields which give you algebraic flows. And likewise in this case. Just what you need is density in the holomorphic case. And then drawer set we call X. We say that X itself has the holomorphic density property if this is true for the Lie algebra of all vector fields, let's say holomorphic or algebraic on X. So if you take this possibly infinite dimensional Lie algebra, you still want to ask that there is that it is densely generated by the complete ones. So for instance, the result of this lemma and so on says that Cn has the algebraic density property and also the holomorphic density property. And then Varolin proved that many other complex manifolds have the density property. For example, if you take such products where K is at least 1, actually L is at least 1. You take products of C star and Cl, this has density property and also algebraic density property. And then it was consequently proved by many people who worked on this, for example, Kaliman and Kuchebaugh. They did most recent work on the subject. They showed, for example, that most complex Lie groups have the holomorphic density property. I think that by now it's true that every semi-simple complex Lie group has the density property. So, so using these things, in fact, using the fact that C star cross C has density property, Wald, maybe I will continue this tomorrow because it's quite an interesting story. Let me just say in words now. Erland Fornes Wald has recently, I think about 2 years ago, it was published last year, using this fact that you have actually lots of automorphisms of C star cross C. And in such case, it's kind of easy to see what would be the complete automorphisms. You would just look at shears like that. But in this variable where you have C star, you could use Laurent polynomials. So just take shears whose coefficients are rational functions. So you take Laurent polynomials in the first variable. So using such, you can show that this has density property. So by using this fact, Wald actually showed that there exist in this object for two Bieber-Bach domains. This means domains of this subdomains here, which are biholomorphic to C2, which, however, fail to be Runge in C2. So it was a long-standing open problem whether every Fatou Bieber-Bach domain, so a domain biholomorphic to all of Cn, is Runge. First examples were made by Wald using precisely these techniques. It's a very simple idea. I'll sketch it tomorrow, but it's very clever. And after that, once you know that you have a non-Runge Fatou Bieber-Bach domain, then you can kind of repeat this construction. So you have a subset of C2, which is like a copy of itself, but not Runge. Then you take again the big C2 and do it again, and do it again, and do it again. You take inductive limit. So by doing an inductive limit, he constructed the first example of what is called a long C2. So a long C2 is a complex manifold which is exhausted by bigger and bigger copies of C2, which, however, in the end is not C2. Moreover, it's not even Stein. It's not even Stein because what you do is you take some little compact set somewhere and you cleverly do it so that the holomorphic hull always goes out of the set to the next bigger set. In the end, you get something whose hull is non-compact. So that was also by itself a very, very old story. It was popularized by John-Eric Fornes some 30 or 40 years ago, this question, but it was only recently solved. So as I say, let's stop here and I say a few things tomorrow.